Hi, we'd like to welcome you to another in a series of webinars designed for departments of transportation. I'm Terry Bills, and I'm the Transportation Industry Manager here at Esri. And today I'm joined by Paul Durdin of Abley Consultants, one of our business partners based in New Zealand. I guess today we owe a special thanks to Paul, who's had to get up even earlier than normal in New Zealand since they just switched off of daylight savings time. So thanks, Paul. Um, Today's webinar is actually part two of a webinar focused on roadway safety and looking at ways in which we can address the issue of fatalities and serious injuries on our roadways. If you didn't catch the first part, you can find it at our website, and we'll give you the link at the end of this presentation. And I should mention that part one is not a prerequisite for what you're going to see today, as they really focus on different areas of analysis. Part one was focused on identifying out-of-context curves, and today's webinar is identifying high-risk intersections in urban areas and identifying high-risk roadways in more rural areas. In both cases, we will see that GIS can make a significant contribution in assisting the safety analyst in identifying areas to target for further analysis. But before we begin, I'd like to point out that we're recording this webinar, and while everyone will be on mute, there will be time for question and answers at the end of the presentation. You can type your questions into the question box, and we'll try to answer as many as time allows. Additionally, the slides, which are part of this webinar, will be available to you on the GeoNet group, Departments of Transportation, and we'll give you the link at the end of this webinar. I guess to start, I would like to repeat a little bit from the last safety webinar, because I think it's important in understanding the approach taken by Abley and their safety work. And in the past, and especially in the US, the focus of safety management was always on changing driver behavior and with a strong focus on driver education programs. But in the late 1990s, independently, both Sweden and the Netherlands began to take a different approach. The Vision Zero approach was developed, and it was officially adopted in Sweden in 1997. And in the Netherlands, the Sustainable Safety Program became the dominant approach in that same year. And both started from an ethical position that human safety should be our top priority and that traffic deaths are preventable. They recognize that humans make mistakes, and as a result, we should really focus on better highway design and ultimately how to make our roadways more forgivable to human failure. And while each of these two approaches took a holistic approach to road safety, each represented a fundamental shift from the prior safety paradigms. Major initiatives that take from these concepts include the UN Decade of Action, which is worldwide, Vision Zero, which we've already mentioned, which originated in Sweden, but now has been adopted by a number of US cities and states. And in the US, the US DOT has initiated the Road to Zero initiative in 2016. The same set of concepts underlies the work that we're going to see today from Abley. It focuses less on driver behavior and analyzing past crashes, but rather focuses on the road infrastructure and how we can identify roadway improvements that would significantly impact safety. And I would like to point again to the great success that this approach has had in Europe. As we pointed out last time, in a 5-year period, Norway was able to reduce road fatalities by 43%, and Greece by 36%. So pointing out what a highly focused initiative can do for highway safety. Key tenets of the Vision Zero approach include, as we've said, that traffic deaths are preventable, and that taking a strong focus on highway safety is really an ethical concern of the highest order. Every traffic death should and could be prevented. In addition, there are also social equity concerns that we should have the same focus and investment for every life. And finally, that a Vision Zero approach is ultimately a data-driven approach, that we use data and monitoring activities to continuously refine our approach to achieving zero deaths. Because safety is such a critical issue, we anticipate having many more webinars on the topic in the future. I hope that we can make this a forum to share best practice and to bring to you some of the best thinking with respect to safety management worldwide. So with that, let me turn it over to Paul and for his presentation. Paul, take it away when you can.
Thank you, Terry, and good morning, everyone. Right, so as Terry's mentioned, this is the second part in this presentation webinar series, and today we're going to be focusing on two areas that are involved in the identification of high-risk locations. The first of these is intersections, and predominantly in urban areas, but the methodology can equally be applied to rural intersections. The second one is in regard to rural roads, and the focus there on utilising non-crash data to forecast crash risk. Before I start on that, though, I thought it would be useful to provide a bit of a comparison between the US and New Zealand. So this chart here shows traffic fatalities in both the US and New Zealand. They're on different scales. So the US is on the primary vertical axis, and you can see that traffic deaths have declined from around 41,000 in 2007 to 38,000 in 2016. Similarly, in New Zealand, we're 2 orders of magnitude different, but that's reflected in the population. We've gone down from around 420 deaths per annum to around, we got as low as 250 in 2013. We were heading in the right direction, but in the last 3 to 4 years, the number of traffic fatalities has increased again, much like it has in the States. And that is largely a reflection of the improving economic conditions, which are known to have quite a significant influence on macro traffic safety statistics. In terms of traffic fatalities per 100,000 population, we can see here that the United States and New Zealand have both been trending downwards until 2013, and then they've been increasing again. The US has declined from 14 and now sits around 12, and New Zealand has gone from 10 to around 7 in the same period. So quite a significant improvement there in New Zealand, around 30% reduction in terms of traffic fatalities per 100,000 population, whereas the States has seen around about a 15% improvement. So the point there is that there's lots of lessons from New Zealand that can be applied to the States, and by no means are New Zealand perfect, but there are some good lessons to be learnt there about what we've done over the past decade to improve traffic safety. So the first risk topic area that we're going to focus on today is intersection safety. And the reason why intersection safety is important is that in urban areas, around 50% of all fatal and serious crashes occur at intersections, and a number of those involve what we would classify as vulnerable road users, so people that are walking, cycling, or motorcycling. And if they get struck in a collision, then they're at much greater likelihood of being involved in a high severity outcome or even death. So improving intersection safety is a globally important issue. In 2010, New Zealand introduced the Safer Journeys Road Safety Strategy, and it adopts the safe system philosophy, which aims to create a forgiving road system based on the following 4 principles: that people make mistakes, that people are vulnerable, you need to share responsibility, and strengthen all parts of the system. The system is defined by having 4 pillars, being safe roads and roadsides, safe speeds, safe vehicles, and safe road use. The safe system approach argues that driver errors should not result in death and serious injury, a condition which requires that road infrastructure speeds vehicles are designed and operated in a way to ensure that in the event of a crash energies are kept below the thresholds likely to result in death and serious injury. Effectively, this means either providing adequate protection of road users against high crash energies through vehicles and infrastructure, or reducing impact and thus travel speeds. The safe system approach does not dismiss individual road user responsibility and requires road users to be alert and compliant. The safe system signifies a change in conversation and a change in culture. It's a change in conversation from a culture of blame to one of creating a forgiving environment that protects system users in the event of a mistake being made. That is quite a significant shift, and it needs to happen across all aspects and stakeholders using the system. So typically, the police, if they attend a traffic crash, will look to assign blame to a user. Now, while that may be required in a legal sense, from a safe system perspective, blame isn't the first port of call. In fact, it should be looking at the extent to which the system acted appropriately or inappropriately in the event that someone simply made a mistake. In July 2013, the New Zealand Transport Agency published the High Risk Intersections Guide. There is a link provided on this slide, and you're more than welcome to go and download the document, which is free on the New Zealand Transport Agency's website. The guide provides practitioners with best practice guidance to identify, target, and address key road safety issues at high-risk intersections. A fundamental principle of the guide is a focus on identifying intersections with an estimated occurrence of future fatal and serious crashes, as opposed to those with less severe outcomes, which supports the Safer Journeys vision. The guide introduces a new technique for identifying intersections that have a disproportionately higher than average risk of future deaths or serious injuries if recent crash trends continue. Their departure from a wholly reactive approach to road safety allows high-risk intersections to be identified and treated before people are killed or seriously injured. The traditional approach of identifying high-risk intersections has been to focus on those that meet the definition of a black spot. While that approach has been very successful in the past, in New Zealand and in Australia and elsewhere, we are now experiencing diminishing returns with the treatment of black spots, which signifies a need for change. By way of evidence, we can see that for Auckland, New Zealand, which has around 16,000 intersections and a population of 1.5 million, so it's a significant city. In 2017, there were 390 fatal or serious injury crashes that occurred at 369 intersections in Auckland. Now, 301 of those, or 77%, occurred at an intersection where there had been no previous fatal or serious crashes in the past 5 years. And 272 occurred at, or 70%, occurred at intersections with 2 or fewer injury crashes in the past 5 years. So what we can see there is that relying on traditional methods to forecast where fatal and serious crashes occur isn't a great predictor. If we were to rely on that crash clustering approach, or where fatal and serious crashes had happened in the past, we would be missing a significant proportion of the crashes, the fatal and serious crashes that happened in 2017. The high-risk intersection guide introduces a technique for estimating the risk of future high-severity crashes by combining knowledge of the interrelationship between speed, crash movements, intersection form and control, and the road users involved. As you can probably imagine, the severity of crashes generally increases with speed and when the intersection form lends itself to high impact forces between vehicles. Roundabouts in particular have a lower crash severity profile than other types of intersections because crash impacts are minimised through controlled entry speeds and acute angles of collision. These relationships are presented as severity indices in the guide. The severity indices represent the observed number of death and serious injury casualties for every reported injury crash of a particular movement type that is then differentiated by intersection type and speed environment. Severity indices indicate which crash movement types for a specific intersection type are more or less likely to result in a high severity outcome. We can see here through these diagrams that in a 50 km/h, so that's a 30 mph speed zone, the likelihood of a pedestrian being killed or seriously injured in a collision with a motor vehicle is around 1 in every 4, so 0.26 is the indice. Compared to a rear end collision, the ratio is 1 to 617, and a side impact collision 1 to 6. So what we do is we take the injury crashes and we apply the different severity indices and then sum those up for the intersections to arrive at risk metrics. There are two types of risk metric that we use in the analysis. One of those is collective risk and the other is personal risk. Collective risk involves the estimation of the number of DSI casualty equivalents based on all injury crashes that have occurred at the intersection in the past 5 years. It is calculated by multiplying the number of reported injury crashes of each movement type by the corresponding severity index and summing these values. Personal risk measures the risk to each person using the intersection and is then divided by a measure of exposure of vehicles travelling through the intersection. This figure shows the relationship between the number of injury crashes and the corresponding collective risk, or the DSI, for all intersections in Auckland. The figure shows that collective risk generally increases as the number of injury crashes increase. However, there are exceptions to the rule, as can be seen here. Those intersections above the dashed line have crash types that have a higher than average likelihood of death or serious injury, whereas those below the dashed line have a lower likelihood. Under the traditional approach to road safety, many actual high risk intersections may have been overlooked from investigation because their overall crash history may not have been considered sufficiently high to warrant investigation. The estimated DSI approach ensures the intersections with the greatest risk of future high severity crashes is highlighted for investigation. At this point in time, if I can draw your attention to this data point here, we'll come back to that shortly as a case study to show that particular intersection. Just by way of data, there were 25 intersections in Auckland that had more crashes in the past 5 years, but on a collective DSI basis, it was by far and away the highest risk intersection in all of Auckland. So I'll come back to that shortly. In order to calculate the risk profile of an intersection, the information required is intersection type and form, speed limit, traffic flows, and the crash history. Given that this information is readily accessible, it's a relatively straightforward process to calculate the risk profile of any intersection. With a sound understanding of the assessment techniques presented in the High Risk Intersections Guide, in my experience, it takes around 30 minutes to source the necessary data and then calculate both the collective and personal risk profiles of an intersection. So there's nothing too hard about that, right? Well, in isolation, this isn't a time-consuming exercise. However, calculating the risk profile of every intersection within a town, a city, a region, or even a country quickly becomes impracticable. In Auckland, for instance, where there are more than 16,000 intersections, if we were to use my estimated time frame of 30 minutes per intersection, this would take an individual more than 4 working years of their life to complete. And so by that time, the crash history used would be significantly out of date. The employee would probably have quit their job, and certainly the need for safety interventions would have moved on. So there must be a smarter way, right? So I want to talk to you about how we've used ArcGIS to risk profile a city, and so in this instance Auckland, and how we've built that in using ArcGIS Desktop and Model Builder in particular. So here's a list of the attributes that are required to calculate the risk profile for any intersection. So we obviously need to know where the intersection is located, its form and control type, speed limit and volume. So all of that information can be sourced from a road centerline dataset as well as a road asset dataset too. Then in terms of crash data, we need to know where the crash happened, its severity, its movement, and the types of users involved, ideally. So the methodology involves starting with road centerline and extracting crash data. In this slide it says from CAS, that's in New Zealand, the crash analysis system, and I realised that in the United States there are different crash databases for every state authority. Then we review the data quality, do a bit of cleaning, create the intersections, and we run a series of models that are built in Model Builder. Now these models assign attributes to all the intersections on the network based on crash data. They assign the crashes to the intersections and crash attributes to the intersections, and then apply the corresponding severity indices so that we can calculate the DSI crash equivalents. The risk metrics are then calculated for collective risk and personal risk, and we output the results and display them in web viewer format, and I'll show you an example of that shortly. So how well does this approach predict crashes compared to traditional approaches? Well, I've recently updated some statistics based on 2012 to 2016 crash information and analysed how well that has predicted 2017 fatal and serious crashes in Auckland. So there were 1,063 intersections with a fatal and serious crash from 2012 to 2016 in Auckland. Now in 2017, there were fatal or serious crashes at 79 of those intersections, so we'll just call that as having a 7% predictive capability at that stage. That's derived from dividing 79 by 1,063. Similarly, there were 903 intersections that had 3 or more injury crashes in that 2012 to 2016 crash period. And of those, there were fatal and serious crashes at 106 intersections, 12% predictive capability. Now, there were 227 intersections that had a high or medium-high collective risk using the DSI method that we've just presented, and there were 41 of those intersections experienced a fatal or serious crash in 2017. So that corresponds to an 18% predictive capability. These numbers are very similar to the last time these numbers were run in 2014. So this really demonstrates that the DSI approach is a significantly better predictor of where fatal and serious crashes occur than traditional methods that focus on raw crash numbers alone, or where fatal and serious crashes have happened in the past. Now, if you recall on the chart, the data point that was sitting highest on the vertical axis, that was the Glenbrook Kingseat intersection, which is located in the rural part of Auckland, high-speed environment, rural crossroads. Between 20 2007 and 2011, there have been 11 injury crashes at this intersection. It had the highest DSI risk in Auckland. In 2012, that intersection was identified and presented to Auckland Transport as having the highest risk in Auckland. Very shortly afterwards, there was a fatal crash and another serious injury crash, which then followed another serious injury crash in 2013 and 2 minor injury crashes as well. Now, Auckland Transport knew that this intersection had a safety problem, but as budgets were tightened around this time, an intervention for this intersection was put on the back burner, and other improvements on the network were deemed to have a higher priority. So this was really a telling exercise in the predictive capability of this approach. Now, to Auckland Transport's credit, they have implemented a significant improvement here. They've changed it from a rural priority crossroads with yield controls or stop controls to a roundabout. And that was installed late 2013, and there have been no injury crashes since. So this really demonstrates the great predictive power of this tool. It was a very unfortunate example that in the period between this being identified and the intervention being delivered, that there was a fatal crash and a couple of serious injury crashes as well. But it really does demonstrate that this is a robust approach and that interventions can have significant improvements to safety outcomes. I'll take you now to the web viewer that we've created for Auckland that shows a lot of this data. So hopefully here you should be able to see a web viewer, Auckland Transport Risk Mapping. This shows a number of different intersections in part of Auckland, and this is the collective DSI risk for various intersections. And we can click on these intersections and see the collective and personal risk profile, the predictive collective DSI casualty equivalents, the personal risk statistics, and based on the total number of injury crashes, and see how these change as we move our way around the network. As I've said before, this is all based on crash data, and we can see the various different crashes that are happening here. So here's all the crashes, and we can click on any of these and we can see that this crash here from January 2015 was a minor injury collision, and it happened on a Tuesday. If I bring up the underlying imagery, so this part of Auckland is on the harbour. We have downtown Auckland out to the left, and this is a very popular cycling corridor out through the bays across the causeway. Now, we've created a number of other metrics to help Auckland Transport, who are the road controlling authority, to better understand types of issues that are happening around their intersections. One of those is a active road user heat map. So this shows locations where cyclists and pedestrians are overrepresented in crashes. And we can see that a lot of those are clustering around the harbour area, and in particular around those two high-risk intersections that we've seen there in the past. The other one is in terms of commonalities, so looking at users and situations that are overrepresented. So here we can see that cyclists are overrepresented, crashes in the weekend, and in New Zealand, being a left-hand drive country, crashes that involve a right turn against collision or a left turn against collision would be the equivalent in the States. Over here we've got cyclists again and the same type of collision. Now it's this information is being used by Auckland Transport to program safety improvements. So this particular intersection here has recently been upgraded from a yield control T-junction to a signalized controlled intersection, and they're expecting to generate significant safety improvements there through the better control of movements at that intersection. Back to the presentation. So the key learnings in regards to the high-risk intersections method are that the DSI approach to estimating high severity crashes represents a shift away from a wholly reactive response to road safety to one that's starting to become more predictive of future fatal and serious crashes. This approach is aligned with the safe system philosophy. Given that transport data is spatially referenced, it can be analysed and mapped in a GIS environment. And the DSI approach identified using the high-risk intersections guide is a very much a better predictor of fatal and serious crashes than historic fatal and serious crashes or injury crashes alone. The second topic that we want to focus on today is rural road safety. Now, rural road safety is a major safety issue, and in the first webinar we looked at high risk curves or out of context curves, and we know that around half of all crashes on rural roads occur on horizontal curves. But how do we know which rural roads are more likely to be the site of fatal and serious crashes than others? One of the key issues that we are faced with on rural roads is that volumes can often be lower. And because of having these fewer crashes, we end up with dispersed crash patterns. And because of this, crash clustering can be an unreliable approach to predict where the next fatal or serious injury crash may occur. One technique that has been developed to predict risk independent of crash data is star rating. Star rating involves the manual coding of more than 50 variables to assess risk along a network. It has been applied in more than 80 countries across the world under the IRAP umbrella, that's the International Road Assessment Program, including New Zealand under the Kiwi RAP banner and the US under the US RAP banner, respectively. Star rating is the gold standard, but it's also the gold investment. So data is coded every 100 meters along a corridor against these 63 primary variables to generate a risk prediction. In New Zealand, the star rating approach had been applied to 7,000 kilometres of the state-controlled network. And New Zealand wished to extend this proactive risk approach to the non-state highway part of the network, but the cost and time involved with star rating was seen to be prohibitive. So in New Zealand, they developed an alternative proactive risk methodology, which has been titled Infrastructure Risk Rating, or IRR. It is a predictive road assessment methodology designed to assess risk independent of crash history, and it is based on star rating. It's designed, however, to utilize existing data sets and omit the time-consuming and expensive collection of data involved in star rating. This approach is very important on lower volume roads where crash history may not be a reliable indicator of underlying safety risk. IRR is a simplified version of star ratings. It is based on 8 key road features and operating situations that have been identified through research as having the biggest impact on road safety. So these are the road stereotype, so that is whether or not the road is divided or undivided. The land use, the adjacent land use, so are we in an industrial area, residential, shopping centre, etc. The roadway lane and shoulder widths, the horizontal alignment, the traffic volume, the density of intersections, the density of access points, and the nature, type, and severity of roadside hazards. Here's an example of the land use categories and risk scores. These scores are based on interactions with adjacent land use. So a commercial strip shopping area has a lot of access points, a high number of pedestrians and cyclists, and therefore a high score. Whereas a remote rural road with few access points and very few active road users has a low score. The scores for each category fit into the IRR model, which is a multiplicative log model, the equation shown in the top right. The score is then used to work out the overall IRR score for a corridor, and these are banded separately for rural and urban environments. IRR is intended to be applied to road sections with uniform features. Here is the corridor segmentation process that we've developed. Firstly, all roads with the same road name and posted speed limit are dissolved into long sections. These sections are then segmented if there is a change in land use along the way. Land use is used as the first order of segmentation, as land use is used to define urban and rural speed environments. Road sections are further segmented based on changes in road stereotype, alignment, and traffic volume. At each stage of the segmentations, thresholds or minimum lengths are applied to avoid segmenting corridors due to short changes in road features, such as overtaking lanes or divided medians on the approach to intersections. Once these homogeneous sections are identified, road features are attached to these sections from geospatial datasets. So here's an example in a rural environment of how segments may be differentiated based on horizontal alignment. This one showing that the road changes from a winding environment to a tortuous alignment. Here's an overview of how all the IRR features are extracted from datasets. So in New Zealand, we have a road asset dataset, which is used to extract the stereotype, lane and shoulder width, and traffic volume information. We use planning datasets to obtain land use information, and we use GIS processes to calculate horizontal alignment and intersection density. Two of the input variables to IRR, namely access density and roadside hazards, can be input manually into the IRR process. But if we're looking to apply this at a network level, we have to make a series of judgments to determine access density and roadside hazards. And we've created some approaches for estimating those, which we have calibrated against manual coding to derive access density and roadside hazards, and found those to be highly accurate. So where has IRR been applied? Well, it has been applied nationally throughout New Zealand, so around 70,000 miles of the nation's road network has been assessed. It's been taken to Australia, and 7,500 miles of state roads in Queensland has been assessed. It's also been assessed on some state roads in Tasmania and Western Australia, which are states of Australia, several other towns in Australia. And we've had a look at some state roads in Utah and applied this technique to 800 miles there, just to see if IRR would be a suitable tool for applying in the states. So let's have a look at how well IRR predicts safety performance. This is based on the 7,500 miles of the Queensland state network, and it uses a statistical binning approach whereby we take the road segments with similar IRR scores, average those out, and then average out the number of fatal and serious injuries per 100 million vehicle kilometres travelled for those corresponding sections. And we can see that IRR is a very strong predictor of personal risk. We can't get much better correlation coefficient than 0.97. So we can see that as IRR score increases, then safety performance deteriorates. Looking at Utah, on the 800 miles of state network that we assessed there, we can see that we get a similar trend and a correlation coefficient of 0.91. Now, interestingly, we had a look at star rating on those same roads in Utah, and with star rating, the higher the number, the better the safety performance, which is the opposite from IRR. And we can see that star rating is a very similar predictor in terms of its correlation coefficient around 0.87. But what this demonstrates to us is that IRR is at least as good a predictor as star rating, if not better. And one thing that I should point out here is that the IRR factors that have been used and applied to the Utah state roads are the New Zealand calibrated factors, so they haven't even been calibrated to the US specific environment to pick up any differences in the way risk manifests in the US compared to New Zealand. So that's a very encouraging sign that IRR is a good tool for predicting crash risk. So now you may ask, well, how is IRR being used? Well, it is being used in New Zealand and in Australia to inform decisions around speed management. As you'll recall from the earlier slides, safe speeds is one of the crucial components of the SAFE system, and managing speeds to a level that reduces impact forces that mean people can walk away from a crash are very important. So the process that is used in New Zealand to identify safe and appropriate speeds involves looking at the functional road classification of the road, the land use, and then it uses a reactive safety metric, so based on actual crashes, their personal risk, and then there's a proactive road safety metric, IRR, is used in that to inform safe and appropriate speeds. Another process, another instance of how IRR is being used is to estimate safety performance and comparing actual safety performance against expected performance from IRR, and we are using that to identify parts of the network where safety improvements are most readily achievable. I'll take you to another example web viewer now. So this one here is the Safer Journeys risk assessment tool in New Zealand. Just bear with me while this data layer refreshes. It's been sitting there static in the background for a while. I'll give it another couple of seconds. Okay, there we go. This should be showing on your screens now. So here we can see the crash risk. This is for part of central New Zealand. This is, I'll zoom out. So this is the North Island of New Zealand, and I'll zoom in here to the Waikato region, which has traditionally had a very poor safety record. I'll zoom in a bit further. This is the city of Hamilton, and it's a population around 200,000 in a rural area nearby. We can see the crash risk and then the infrastructure risk rating for segments adjacent to that, and how that combined with the road classification can be used to generate safe and appropriate speeds. We can see here that the black lines are 100 kilometers per hour or 60 miles per hour, and the red lines are 80 kilometers an hour or 45 miles per hour in terms of safe and appropriate speeds. Using relationships regarding the change in operating speed that may occur if speed limit changes are made, we can use that to identify the highest benefit safety opportunities on the network. So these are these corridors here, and we can start to use that to develop estimated DSI savings if speed limit changes are made. So on this one here, Piarco Road, we can see that there have been 2.56 DSI equivalents in the past 5 years, and we'd expect to save around half of those if the speed limit change was made, and that is simply a result of changing the operating speed, which would lead to fewer crashes and less severe crashes as well. So all of this information is being used by the New Zealand Transport Agency and the local authorities to develop their speed management implementation plans to take out for community consultation. So the key learnings in relation to the rural roads are that crash history is a weak predictor of future crashes on low volume rural roads. IRR, by contrast, is a strong predictor of personal risk and at least the equal of star rating. IRR can be calculated for a fraction of the effort and the cost of star rating on networks with sound road asset databases. It's being used to inform speed management decisions and to identify safety improvement opportunities in New Zealand. And the proactive approach to safety is ethically responsible and aligned with Vision Zero and the SAFE system. Now, that's the end of my presentation, and I'll hand back to Terry, and more than happy to answer any questions that he has been fielding during the course of the webinar.
Okay, thanks, Paul. We do have a few questions, so let me start off. The first question actually references some California crash data, but it says, other than crash data, what data sources are important when analyzing traffic injuries and fatalities? And that really came in on the first section on intersection analysis.
Yeah, look, that's a good question. So in isolation, crash data has only, I guess, moderate value, and we need to put that within a context. So we need to understand the type of intersection form, whether it was a 3, 4, or 5 or more leg intersection, what the type of controls that exist at the intersection, whether it's a signalized or a yield control or a roundabout, and also the speed environment, because all of those factors, the speed, the intersection form and control, have an impact on the likelihood of death and serious injury for a particular crash movement type. So we need to understand those features as well as those commonalities amongst crashes.
Okay, and maybe you could just say just a little bit more about kind of the difference in terms of the approach, why your feeling is that, you know, past crash data is not going to be a good predictor. And, you know, unfortunately, I think that's really kind of informed a lot of our current safety analysis as we look at past crashes and we use that to identify. And so, again, maybe just speak a little bit more about really why this approach is, I think, you know, much richer and gives us much greater analysis.
Yeah, okay, look, again, that's a very useful point. I guess the traditional approach has been focusing on sites with a large number of overall crashes. Now, what we find with those is that in a lot of instances, they may be of a type and a severity that generally result in minor injury crashes. Now, there's nothing wrong with trying to reduce crash incidents, but if the crashes are of a type that have a low likelihood of being future fatal and serious crashes, if those trends continue, then there's limited future benefit attached to those. Whereas the new approach says these crashes indicate that if those crashes continue, much like that Glenbrook Road, Kingseat Road intersection we looked at, that if those crash trends continue in the future, we have a very high likelihood that we will see fatal or serious crash outcomes occurring, and they're the ones that we want to be prioritizing for investigation and intervention, because we remember the safe system philosophy is all about reducing high severity casualties and not necessarily about reducing crash numbers in totality. It may seem like an odd thing to contemplate, but safety, we can actually achieve good safety outcomes without reducing the number of crashes if we can reduce the severity of those crashes that happen on the network.
Okay, yeah, thanks. Another question really having to do again with your intersection analysis. Are you intersection collisions taken into account major or minor or both types of intersections? So how do you do your analysis on all intersections or?
Yeah, another good question. So the approach is applicable to every intersection, major and minor. The personal risk component of the metric takes into account the volumes and the exposure metrics. So that effectively standardizes risk on a per user passing through the intersection basis. So intersections that happen at crashes that happen at major junctions, you generally need to see more of those happening and a greater likelihood of death and serious injury compared to at a minor junction for those to be rated differently because of the exposure that's taken into account in the personal risk metric.
Okay. And then maybe you might want to, I know, Paul, you and others from Abley have actually spent a little bit of time in the U.S. How can people reach you, and how can they sort of take advantage of some of the research that you've been able to do in New Zealand and elsewhere? How could they take advantage of that in the States?
Oh, look, absolutely, Terry. People are more than welcome to get in touch with me, either via phone or email. My contact details are provided on the slideshow, and I'm more than happy to answer any questions, point them in the right direction for resources in terms of all questions, or to carry out work for them. We've obviously got a relationship with Esri, being an Esri business partner at Abley, and we're looking to take our risk assessment techniques in the road safety area globally, beyond just New Zealand and Australia. And we see the US as being a really good opportunity to apply these network assessment techniques to help DOTs and other road controlling authorities to prioritize their activities to improve safety outcomes.
Okay. If other questions, please submit your questions through the question pane. We are showing the additional resources, so you can find the prior webinar on the Esri transportation webinar page, a few other examples, and the references to some of the work that Abley has done in New Zealand. Paul, any final thoughts before we wrap this up? And we certainly, again, we owe you a great debt of gratitude getting up so early over there. But any final thoughts?
Well, I think one of the key things, and maybe I haven't mentioned it here, is the benefit of conducting this analysis at a network level is that it allows you to prioritize and understand risk across your network. And what that really means is that you can ensure that you're capturing the highest risk opportunities at a network level and directing energy and resources to address those. Now, that's different from a corridor by corridor or intersection by intersection approach, which doesn't allow you to prioritize at a network level. So these techniques using ArcGIS and the various tools that are available are really powerful for understanding that risk at a network level.
Okay, well, with that, we'll close this off. Paul, again, thank you very much. And obviously, we hope to have you back in a future webinar where we can further explore some of these concepts. We thank all of you for being on today, and we hope you'll join us for future webinars. So, okay, with that, thank you. Bye-bye.